Hey everyone! If you've been curious about what studying physics is like at UCL, look no further than this video. I'm an astrophysics master's student, and I'm here to tell you about my favorite module out of the 6 I picked. Let's talk about the physics of exoplanets. What are exoplanets anyway? The term combines the prefix exo, meaning outside or external from the ancient Greek, and the word planetes, also from the Greek, which means wanderer. This reflects how they observed that these celestial bodies move differently than stars. Essentially, exoplanets are planets outside of our solar system. But how can we detect them anyway? There are actually several techniques, from transits, radial velocity, astrometry, microlensing, and even direct imaging. Let's go through a few of these, what are the best ones, and what kind of planets can we detect with each. Let's start with one of the most popular methods, transits. When a planet orbiting a star steps in front of it from our point of view, it causes the brightness of the star, or flux, to decrease, something we can detect from space. Knowing the radius of the star and the flux difference, we can determine the radius of the planet. This means this technique favors planets closer to their stars, or with inner orbits, and with large radiuses where the flux difference will be more easily noticed. Another method that can actually be combined with transits is called radial velocity. A planet that orbits a star suffers a gravitational pull from the star, but the reverse is also true. The star also suffers a gravitational pull from the planet, although much smaller given the differences in mass. In fact, both bodies orbit a common center of mass, the point where both bodies' gravities balance each other out, which is not at the center of the star. This means that although much smaller, the star has an orbital motion of its own, sometimes called a wobble. Like transits, this wobble can be detected from space, which produces graphs like this one. From here, we can extract the velocity amplitude and the period of the wobble. Assuming conservation of momentum and knowing the mass of the star, we can find the mass of the planet. Combining this with the transits method, we can actually find the planet's density. This tells us if it's a rocky planet like Earth's or a gaseous planet like Jupiter. This method favors more massive stars and with inner orbits as well, as both of these factors will produce a more frequent wobble of the host star, which consequently produces a higher radial velocity amplitude. Last but not least, let's talk about my favorite method. It is not one of the best, but the physics of it absolutely fascinates me. Let's imagine you and a friend stretch a tablecloth. If you place a ball in its center, the tablecloth bends. This is what happens in space, where any celestial body's gravity will bend the fabric of space-time. Now, if you have a background star and a star traveling in front of it, the traveling star will actually bend space-time, and the light from the background star will curve around it, creating a ring when observing it. Like so. Here you also have the case of a black hole lensing a galaxy. This is what is called microlensing, and the detectable effect is an increase in brightness, or in other words, an increase in magnification. Now, if that traveling star has a planet, you will have 2 magnification events, which helps us detect exoplanets. This method is not the best, as these events occur very rarely, and only provide information on one particular location of our galaxy. Usually, we observe towards the center of the galaxy, as the likelihood of another star crossing another is higher. That's the science. Now let's talk about what the course itself is actually like. I had 2-hour-long lectures once a week, but the lectures were kind enough to give us a break after 1 hour. We were also given 1-hour-long tutorials once a week, where we were given questions to solve, and the lectures were around if we needed any help. It was a great opportunity to actually engage with the material, and we were even encouraged to work in groups. Now, in terms of assessment, we had 3 courseworks, which in total were worth 10%, while our exam was worth 90%. It might seem like a lot, but the exam went really well for me, so I know you can do it too. Hopefully, this made you interested in studying at UCL, or you've at least learned a thing or two about exoplanets. Either way, stay curious. Goodbye for now!